Okay, you can start.
Okay.
Give it less than a minute. I'll go upstairs and you'll have to listen.
Okay, so last time we were talking about atmosphere and different characteristics and structure. Let me just write this email for you guys. If you have any questions or if anything's really confusing, just send me an email. Here's the link right here. So I know this stuff can be confusing. Okay, there we go. But yeah, I just want to review some of the stuff we went over last time, just in case you were confused. I added some new slides, so hopefully it'll make this more clear for you. Yeah, we basically went over what is the atmosphere made out of, and you'd think, you know, since you breathe in oxygen, that it would be mostly oxygen, but that's not the case. It's mostly nitrogen. You have these other molecules that are in the air in the form of gas. Oxygen and nitrogen are the main two. Nitrogen, you can see from this chart, is most of what the air is made out of. And you also have carbon dioxide. This is what we breathe out of our lungs. Argon in this small amount, and then this is the other gases, which might be helium or other elements in very small amounts, but they are very important, so we include them in this pie chart. We talked a little bit about this before, but the ozone is made out of 3 oxygen molecules, O3, and this kind of third oxygen really is special, and it makes the ozone what it is. This is not what we breathe in, but this is a different molecule, and you can tell that there's 3 just because of this little 3 that's here. We haven't talked a little bit, but hopefully today we'll get to human influence. How are humans affecting the atmosphere? And in the last 10 years, this has become a really huge topic. People have been researching and learning much more about this because it's becoming a big part of our lives, and it's really affecting us a lot. So hopefully we'll get into more detail today about this. We talked about transportation is a big part of the human influence. Carbon monoxide, which is just a scary way of saying CO, just 1 oxygen and 1 carbon. And this is just what comes from our cars mostly, cars and motorbikes, or scooters, whatever you're thinking about, things that we use to transport us around, buses and everything else. So most of this, you can see, is from what moves us around the city. So this is kind of where we left off. We talk about the atmosphere versus the altitude, and we know that down here, this is sea level, this is the top of Mount Everest, and this is way up, in the upper parts of the atmosphere. And we know that as you go up from sea level, the atoms in the air get further apart. The air becomes thinner. So when you're at the top of Mount Everest, or not even at the top, there's half as much air than when you're at sea level. So this is really important to think about. And then when you come up to 36 kilometers, which is basically outer space, you have almost no air. So the molecules are really far apart up here, and down here they're what we know is really close together. So if you try to run 1 kilometer on the top of Mount Everest, you're going to be really, really tired. Whereas hopefully if you run 1 kilometer on the surface, at sea level, you'll be okay. Okay, so we talked a lot about this last time, and I'm hoping that this time it's kind of going to be jump-starting your memory about the layers of the atmosphere. we kind of know that the troposphere is the first layer. So the temperature goes down as you go up. So this is where weather happens. The top of Mount Everest is really cold. The bottom is much warmer. This is all considered the troposphere. Okay. The stratosphere is where we talked about a little bit last time. The radiation from the sun is mainly absorbed in the stratosphere. The radiation that comes from the sun, the energy that comes from the sun, would be really harmful to all the life on Earth if it wasn't kind of blocked a little bit by the stratosphere, which is the next layer. We talked about the mesosphere is the next layer, the third layer, and this basically is where like comets would burn up if they were to come in from outer space. If you see a shooting star, it's generally being burned up in the mesosphere, and this is the third layer. The thermosphere is where you see those kind of really cool pictures of lights in the sky. The aurora borealis, we talked a little bit about that last time. It's where radiation from the sun is exciting oxygen molecules. So these oxygens are getting really absorbing energy, and they're producing these really fantastic colors. Other gases as well are being affected by the sun, and we get these colors in the sky. We talked a little bit about that. I've added this diagram. Hopefully this helps you. This kind of tells you about the layers of the atmosphere. So this is everything we just talked about. I mentioned a little bit last time there's a fifth layer called the exosphere, and that's basically just the border between all of these layers and space. So you can see it says, mesosphere is here, troposphere is here. You can see these kind of mountains. This is the Earth down here, so up to about 14 to 18 kilometers above the Earth. That's all the troposphere. So this is, if you go above this, there aren't really any clouds. You don't have storms really up here. This is pretty sunny, nice weather if you make it up there, but the air is very thin. The molecules are getting further and further apart as we go up. This pink band right here is ozone, and like we talked about, that's O3. And the ozone is very, very helpful in blocking UV radiation. And UV is just a type of energy that comes from the sun, and it's basically what gives us a suntan or a sunburn. And if you took away this layer, we would be in big trouble because the sun would be burning us very, very badly pretty much anywhere. So yeah, this is another diagram. This is kind of confusing, but just know that the temperature doesn't always just decrease as you get higher in the atmosphere. It kind of goes back and forth like this, and this is because each layer of the atmosphere is different levels of gas, and they're different amounts and different types. So kind of chemically, the difference between these layers causes the temperature to either decrease. So like we said, going from sea level to the top of Mount Everest, we have the temperatures decreasing. But as you go above the clouds, above the troposphere, into the stratosphere, what's happening here? The temperature is actually the same. You could go up, it looks like about 10 kilometers, and you'd have the same temperature right around, negative 55 degrees Celsius, which is really, really cold. And then as you get up past the ozone, the temperature starts rising again. And this is because you're no longer protected from the ozone. You're exposed to the sun really, really directly. So as you go up closer to the sun, it gets hotter. The mesosphere goes back down again, and then the thermosphere, where you get these oxygens and different gases heating up and being excited, producing these colors. The temperature goes back up again. So don't worry about memorizing this chart. Just know that the temperature goes down and up and down and up. It doesn't, it changes as you go, up in the different layers. You'd expect it to kind of go like this. You'd expect it to just get colder and colder as you went up, and then space is, freezing cold or whatever. But that's not the case. It changes like this. Okay, so this is pretty confusing if you don't have kind of a lab or a way to kind of show this with tennis balls and things like that. But I added a few slides and we can go over this again, so hopefully it's more clear. Characteristics of the atmosphere, including Earth and Sun relationship. So this is how the Earth is affected by the Sun. The Earth affects the Sun, but in a very small way because the Sun is so huge. It's barely affected by the Earth, but the Earth is hugely affected by the Sun. If we didn't have the Sun, there would be no life on the planet. We wouldn't exist at all. So how does Earth move, and what is the significance of that? Why is that important? Really, Earth moves in two main ways. It moves in a rotation and it moves in a revolution. So we went over this before, but if you imagine the Earth with a kind of a spike going through it, it rotates around itself like this. That's rotation. And then if you have the Sun over here and the Earth over here, the Earth moves around the Sun. So that's revolution. Revolution and rotation. And it does the same thing. It does both of these things at the same time. And this is kind of why the Sun affects different parts of the Earth in different ways. And this is where we're going to talk about seasonal changes. So this is a picture that we saw before. It talks about that the Earth is actually not straight up and down. It's kind of turned to the side, and the Sun shines differently on different parts of the Earth. So we know that in some parts of the world this can be really extreme. You have summer and winter. You have these different seasons. The two that we're going to talk about first are the summer solstice and the winter solstice. So you have basically the thing to take away from this is that in the winter there's more darkness than light. So we're talking about here that if you're on the northern part of the Earth, so above the equator, which is this line right here, hopefully you've heard of that word before, as this Earth rotates, more darkness per rotation. For every one rotation, there's more darkness than light on the northern part. And if you move the Earth so that it has this revolution, it moves over here. If it's on this side, this takes about 6 months, half 1 year, to move from this side to this side. And then you have the opposite. You have more light than darkness in the northern part of the Earth. So hopefully this makes you understand this a little bit more. And like I said, if you feel like this is totally confusing, you can go on YouTube and look at Earth and seasons, and there's a lot of videos that should be pretty helpful about this. But I highlighted in red here. What's going on? It's kind of like reveal the slide. So hold on one second. We're having technical difficulties. This computer is way too smart. Oh, there we go. Okay. So you have more darkness than light every day in winter. And this is kind of every day or each day. So the Earth is always going to be having this revolution, and it's always going to be rotating. So you can imagine it rotating around this kind of line right here, and it's kind of tilted. So I know that's a lot to think about, but just kind of, this is a very important slide, and just go back to it. You can access these slides on the website and review them after this if you want. Hopefully that'll make things more clear. But So over here in the north, as this rotates one time, you're going to have more shade, more darkness than light. And this is wintertime, okay? And over here, this is summertime. So this is the shortest day in the year, and this is the longest day in the year, assuming you're on the north side of the earth. Okay, so as this earth moves from summer solstice to winter solstice, or winter solstice to summer solstice, the amount of darkness each day is changing. So as you move from winter in the northern hemisphere to summer in the northern hemisphere, the daytime is getting longer. Okay, and we'll talk a little bit more about this if I can figure out how to work this slide machine.
Yeah, just flash.
Okay. So then we have the equinoxes, and we'll kind of review what I just talked about again. But you have the solstices, which is the summer and the winter, and then you have the equinoxes. And this is kind of a big word, but this is just called the autumnal equinox. And if you've heard the word autumn, it just means fall time. So this is halfway in between winter and summer, and the same with spring equinox. And you can kind of tell because this equinox is kind of like equal. And if you want to do, some counting, you can say that September and March are exactly 6 months apart. Okay, so we just saw here that this is about 6 months to go from here to here, and you're gonna have over here you're gonna have an equinox, and over here you're gonna have an equinox. And we can see that in this next slide, okay? So during each equinox, there's an equal amount of light and darkness. So over here, right, we have more light than darkness in the summer. Each equinox, doesn't matter which one, during this point in time, there is exactly the same amount of light and darkness each day on Earth, everywhere. So it's pretty cool. It doesn't matter where you are on Earth. There's the same amount of light and darkness. There may be, this only happens 2 times per year. So what's happening between vernal equinox and summer? So these days are really short over here. As you move towards the vernal equinox, the days become longer and longer and longer until eventually they're equal. And then the days become longer than night. There's more light than darkness, okay? And then you get to summer solstice. So again, this is new information, and it might be confusing. It was definitely confusing when I first heard it years ago, but just maybe review this slide and check this out, and really if you see this in motion, maybe it will help as well. But I've tried to make it as simple as possible here. The vernal equinox is the midpoint between winter and summer. So as you move from these really short days to equal amount of light and dark, and to really long days, the midpoint is the vernal equinox. And as you move from summer to winter, you have the autumnal equinox. I feel like this should just say fall equinox, but for some reason someone wanted to name it autumnal. It's kind of a hard word to remember, but just remember autumn and fall. This is just someone trying to sound smart, so don't worry about that. Yeah, fall would be better, I think, but people are disagreeing with me in this room, so I guess that it's been an ongoing argument for a while. So yeah, this is just a verbal way of saying what we already said. The length of day compared to the length of darkness is determined by the Earth's position in orbit. So position in orbit just means where is the Earth in relation to the sun, and what does it look like. So right now, it's tilted. This is the axis here in red. The Earth is spinning around the axis, and it's revolving around the sun. Okay, so based on where it is, changes the length of day and the length of night. Okay, as it moves towards the summer, the amount of daylight increases. As it moves towards the winter, the amount of daylight decreases. Okay, so yeah, again, if you find this confusing, please send me an email or consult Wikipedia or YouTube. So yeah, this basically is a little bit more detailed. It tells us the dates, and things like that. And you'll notice that the important part about this slide is that everything is 6 months apart. So you have, if you say 12 months in 1 year, between the solstice and an equinox is 3 months. Okay, 3, 6, 9, 12, and between, the summer solstice, depending on where you are, the winter solstice, you have 6 months as well. Between June and December, 6 months. Between September and March is 6 months as well. So hopefully with the 4 different visuals, you will maybe start to understand. Okay, so this is kind of new information from last time. Energy transfer as heat. So people tend to confuse heat and temperature. Heat is, movement of energy. And we're going to talk about why this is and how this works in a lot of detail this next term. It can be kind of confusing, but it's essential to life as we know it. So energy is movement of heat between one object to another. Okay, and it can only happen when the 2 objects have a different temperature. So this diagram over here shows kind of some older heating methods for houses. This is called a radiator right here, these things. And hopefully from previous physics or something that cool air moves downwards and hot air rises. So you get this kind of cyclical circular effect between this cool and warm air. And this is just to show you how energy is moved. So this cold air moves past this radiator, which is hot. Okay, this is okay. So this kind of blue just shows that this is cold air. It's moving past this hot radiator, and it's kind of moving up. And as it moves past, it is absorbing heat from the radiator. The heat is moving from the radiator to this air, and it's heating it up. And the same thing happens between the sun and our atmosphere. The molecules, the oxygen, the nitrogen, the helium, carbon dioxide, all of those things are heated up by the sun, and the atmosphere moves as well. So we have these kind of patterns on Earth. Weather is produced by this kind of pattern in a lot of ways, and then you have this heat kind of being released, okay, which also happens on Earth. So you can kind of think of the atmosphere as this house, and this is just the movement of air. It's being warmed up and cooled down, and these radiators could kind of be like the sun. And here's just another diagram. If you don't understand this, or just to make this more clear, you have 100% solar radiation. So this is the sun up here, and it's kind of emitting this energy in the form of radiation. And radiation is just electromagnetic waves. We'll go over that in a little while. It's the same heat that you could feel from a fire is radiation. So just think of the sun as a gigantic fire, and it's kind of releasing its heat in the form of radiation into the atmosphere. And we have this is 100%. So if you want to do the math, you can add up all of these percents and you'll get 100. So basically, most of this, about half, is absorbed by the surface of the Earth. Okay, almost 20%. is absorbed by the atmosphere and the clouds. So this is water vapor, all the layers of atmosphere that we talked about at the beginning of this lecture, and any other gases are going to be absorbing heat. Just like in this house diagram, this heat is moving into these clouds. They're cool and they become heated up. Some of it's reflected by the atmosphere, just like if you were to shine light onto a mirror, it's kind of bounced off of the atmosphere. The clouds don't absorb all of it. See, they actually release or reflect more than they actually can absorb. So 20% as opposed to 19 is actually bounced off of clouds. And then just have usually the dull surface of the earth, and in particular water is really good at absorbing energy, and it's not as good at reflecting. So only 4% is reflected by the surface of the earth, and this includes water. And because water is so good at absorbing energy from the sun, this is why we have this huge amount of energy, heat, absorbed at the surface, and it's kept there by the water. And we could do an entire lecture on water and why it's so awesome and everyone takes it for granted, but I'll save that for later. But hopefully these kind of help you understand heat and the fact that this has nothing to do with temperature. We don't care about how hot this part of the surface is, or how hot this radiator is. This is just talking about the movement of energy, and this is heat. Okay. So yeah, this is the same diagram if you need a bigger blow up of it. So temperature, I don't mean to say that temperature is not important, because it definitely is, but this is much more specific. You may have seen this on a really bad day. It's basically measuring how hot your body is. And you put this in your mouth, and then you don't have to go to school, which is sweet. But anyway, temperature is basically a measurement of, how fast are molecules moving. So this is just an example, but if you have this kind of box filled with gas and you heat it up, you can kind of see these molecules are kind of just moving kind of slow. They have this kind of low temperature. And then as you heat this up, these molecules are moving faster and they're bouncing into the walls and each other, and this kind of movement creates an increase in temperature. So this increases heat, and the heat creates an increase in temperature. So the more heat that you have, the greater the temperature. So temperature is how we measure, give a number to the amount of heat. So this is, just to go back, this is like the process. The movement is the heat, and how hot is it is the temperature. Okay, so how is heat transferred? We just talked about how heat kind of interacts with the atmosphere, but are there any other ways that heat moves? And there are three main ways. You have conduction, convection, and radiation. And I used the word radiation before, talking about the sun. This is the same kind of thing you feel when you stand next to a fire and you feel the heat or warmth coming from the fire. Convection you may have not heard before. This is kind of very nice diagram about the three types of transfer of energy. If you have this stove and it's heating up this pot, that is conduction. This is transfer, directly contact between the stove and the pot. Or if you were to touch this, if it was metal, which hopefully it wouldn't be if it was good quality, but if it was metal and you touch this and burn yourself, you were burned by conduction, and maybe that would help you feel better, but you know that this is what was happening. Convection, which is one that isn't used very often, this term you may not know, it's just kind of the heating up through some sort of liquid or substance. So if you have the heating up of gases or mostly we use this term for liquid, and it's the transfer. So, you know, this pot is filled with water. The bottom layer of the water is going to be warmer than the top layer. You have a huge pot of water as this thing is heating up. So you know, you have this example with steam here as well. You know, it's the hottest down here, then warm, and then kind of cools off as it gets open. And then, like I said before, radiation is the energy transferred by, you know, electromagnetic. This sounds kind of redundant. So yeah, just electromagnetic waves. Kind of, you can see these wavy things here. But don't worry about this. Just, you know this is kind of like the sun, radiation. Okay, so the sun has electromagnetic waves coming off of it. This is what heats up our atmosphere. This is also what causes a tan. Really, the important thing is that, you know, there's a huge spectrum of light or electromagnetic waves coming from the sun, and only some of it heats up the environment, some of it causes colors in the atmosphere, some of it we can't see or feel at all. It's part of a large array of energy. So this is called the electromagnetic spectrum. This is a really scary word, I know, but it's very important. It just refers to the waves that come from the sun, and you know, we'll see this in a second. So the sun is the reason that we have light on the earth, the reason we can see things during the daytime. And as you can see, this whole band right here is the radiation, electromagnetic waves that are coming from the sun. Okay? Or coming from, you know, certain parts of the earth to other parts of the earth. But just think about kind of this is all waves, all these things. Radio waves, you know, you have microwaves, infrared, light that we can see, UV, ultraviolet, which is suntan, sunburn wave, X-rays, and gamma rays. So, you know, it's important to know that this little tiny band right here is light we can see, visible light. And if you look at this kind of spectrum here, down at 0.4 you have like blue and violet, and up here you have red. You can see this looks kind of like a rainbow, and basically it refracts, light comes in and it excites different molecules, and it kind of produces these different colors. And these are the lights that we can see. And you know, hopefully you've seen one of these before. They're really nice and beautiful. Basically what happens is light from the sun, electromagnetic waves from the sun come in, and they hit these water molecules that are in the air. So this kind of happens when it rains or over a lake or something. You know, these are water molecules in the air, and they take these different wavelengths. Okay, so you can see that down here you have these short wavelengths. The wavelength is the distance between here and here is the wavelength. So, you know, this wavelength over here is really short. So that's why we call these short wave and long wave. So these are all different wavelengths. You have 0.4, 0.5, you know, 0.6, 0.7. So as these change, you get the different colors, and that's what forms a rainbow. And it's really cool to think about, you know, why these things form, and basically every color that we see on the planet comes from the reflection of light from the sun. So if you're looking at a blade of grass, and it's probably going to be green, and that's because plants reflect green light. Light that is green bounces off of them, so they absorb all this light from 0.55 to 0.7, and from 0.4 to about 0.5. They absorb all of that light. They cannot absorb green light, so they don't need it. So they kind of release it. It gets bounced off from the sun. That's why this color green exists. So if you think about colors, you can say that if you're seeing the color with your eyes, it is being bounced off of whatever you're looking at. So, you know, my shirt is blue. That's because, you know, the light that's coming off of my shirt, you know, the light's coming through the window, it's hitting my shirt, and then it's bouncing off blue light, which is just this very, very specific band of light. Okay, so pretty interesting. I find that stuff really cool. If you want to look it up more, just feel free to check it out on Wikipedia. You can find all kinds of cool things about light, and you can also take these words and look each of them up if you want, and you can find out what they do. We all know, you know, microwaves are really cool. They make, you know, noodles and stuff. This is electromagnetic waves, same kind of waves that come from the sun, and they just have a different wavelength, and this produces you know, the heat that heats up our noodles when we want to eat. It's pretty interesting. Okay, so this is kind of the textbook definition of radiation. You know, transfer of energy through space by electromagnetic waves. So the ones we're talking about are just, you know, examples of that. So we have, you know, this is the key. Transfer as heat. So the movement of energy is heat. If you can kind of grasp that concept, this will be a lot easier to understand. All of these things have to do with the movement of heat. And, you know, unlike conduction and convection, which need material to travel through, so the heat coming from a fire or coming from the sun, it can travel through space. So you can't have the same, you know, so with convection, we have this heat traveling through a substance, either a gas or a liquid. Conduction, you know, two objects are touching, and that they kind of move heat between them. And, you know, radiation is very, very special, because radiation is what, you know, transfers heat through anything. It can move through space, and this is because these waves do not need anything to travel through. They don't need water, they don't need metal, they can just move through anything. They can move through space very, very easily. And this is how, you know, this energy gets from the sun to the earth. It's really amazing that something so far away could transfer this amount of energy. So radiation is in its own league. It's very, very special. And it's definitely the reason that we exist today. Without radiation, there would be no people, no plants, nothing like that. So yeah, just to take away from this, radiant energy, which is just a fancy way of saying radiation, can travel through the vacuum of space. So these other forms cannot travel through space. Okay, so another cool thing about radiation, this is just kind of the details of it. I wouldn't worry about committing this stuff to memory. You don't need to memorize this. But just know that radiation isn't just heat coming from the sun. It's also energy coming from you. You know, energy coming from the computer. So what you're looking at right now, you're looking at this computer screen. The screen is emitting energy, you're emitting energy, and this is all radiation. This is heat that's moving, radiating from your body. So your body cannot maintain all this heat. It can't just trap this heat. It emits this heat, and it moves out in these wave patterns from everything. This pen, okay, has radiation coming off of it. It's got some kind of heat, and the heat is moving away from it. There's heat coming into this pen. It's everything around us has heat. All objects at any temperature. You can have an ice cube has heat coming from it. It has heat going into it. They all emit radiant energy. So this is totally mind-blowing. It's really cool. If you don't understand it, you know, that's fine. It takes a little while to understand, you know, how heat works. But, you know, obviously, objects that are really hot radiate more energy. So a fire is going to radiate a ton of energy. That's why you can just put your hands up and, you know, you get warmed by the fire. But an ice cube is not going to really, you know, radiate too much energy, not enough for you to feel because it's cold. So really hot things produce short wavelengths, okay? So gamma rays, okay? These are the shortest waves. Remember we talked about the wavelength is the distance between here and here. When you get all the way to these very short waves, you have gamma rays, and they're pretty dangerous. They produce the most heat, and they can really be, you know, if you don't want to get in the way of a gamma ray, because that's going to really hurt you. But yeah, that's not too important. Just know that the wavelength kind of is different based on how hot these things are, or where they're coming from. This is this last point here is something that people all the way through college physics can't handle. This is a really confusing thing. It says objects that are good absorbers of radiation are good emitters as well. So this means that if something can absorb energy very, very well, then it can also release energy very, very well. And you would think that if something wanted to take energy in, it wouldn't be good at releasing the energy. But this is not true for radiation. You have these objects that are absorbing can also emit really, really well. So say you have you know, a piece of metal that's really good at absorbing energy. A good conductor would be really good at absorbing energy, you know, in any form, and they're going to be able to release that. Once they get to a high energy, when they become really hot, they cool down quickly as well. So this is very confusing for a lot of people. So if you don't understand it, then that's fine, because, you know, people that are studying physics in college have a hard time remembering this as well. But just know that good absorbers are good emitters. You know, just don't think about it too much, or your head will start to hurt. Okay, I'm going to end there just because this is kind of a good note to think about. And just like I said, you know, think about energy transfer. How is energy moved? And that's what heat is, the process that we're talking about. And if you go back and you look at the effect of the sun on our atmosphere and on our Earth, you can kind of see that the heat is going to be the movement of energy. The temperature is going to be the amount of heat. So just if you take anything away from this, just remember that heat and temperature are different, and that's why. There's hopefully the seasonal diagrams will help you understand summer and winter and fall, but don't worry if they don't. We're going to go over this in class, and I'll have a really cool in-class diagram to show you guys, so we can kind of grasp that, because it's difficult for a lot of people. So yeah, I'll see you guys next time. Okay, bye.
Yourself, then
Okay.
you want water?
Yes.
Down, you can
Have this.
sure.